Hello everyone, welcome to my channel. In this video, I will discuss the molecular orbital theory of some heteronuclear diatomic molecules or ions like CO, NO, NO+, and Cn-. In my last two videos, I have discussed the molecular orbital theory of homonuclear diatomic molecules. If you are interested, you can go through those videos as well. So, let's start. In the valence bond picture of carbon monoxide, it has been proposed that one dative bond or coordinate covalent bond is formed from oxygen to carbon, giving a triple bond character between the carbon and oxygen atoms in carbon monoxide molecule. So, we may consider both carbon and oxygen are sp hybridized in carbon monoxide molecule. We will use this hybridization concept in drawing the molecular orbital diagram of carbon monoxide as well. Now, let us consider the electronic configuration of carbon, which is 1s2, 2s2 and 2p2, and then for oxygen it is 1s2, 2s2, 2p4. We will take the valence orbitals, that is 2s and 2p orbitals of carbon and oxygen for drawing the molecular orbital diagram. The 1s orbitals will also form the lower energy molecular orbital sigma 1s and sigma star 1s, and that will be the kk cell, and which will be positioned below the main molecular orbital diagram. You will understand that when I will show the full molecular orbital diagram of carbon monoxide. Okay. Now, let us take the 2s and 2p orbitals of carbon at the left hand side and the 2s and 2p orbitals of oxygen at the right hand side. Please note one thing, that the energy difference between the 2s and 2p orbitals of carbon is much less compared to the 2s and 2p orbitals of oxygen. Okay. And another thing is that the 2s and 2p orbitals of oxygen will be much more stabilized compared to the carbon atom, because the electronegativity of oxygen is greater than carbon. These atomic orbitals of carbon and oxygen will produce some hybridized orbitals. Like for carbon, there will be two sp hybridized orbitals, psi sp1 and psi sp2. And if we consider x-axis as the molecular axis, then 2py and 2pz orbitals will not participate in the hybridization process, and they will be like this. Okay. Similar is the case for oxygen. Here also we will get two sp hybridized orbitals, and 2py, 2pz will not participate in the hybridization process. However, one thing you should remember, that because of the energy gap of 2s and 2p is less in case of carbon, the interaction between 2s and 2p orbitals in case of carbon will be much greater than that of the 2s and 2p orbitals of oxygen. And this one, that the lower energy psi sp1, you may consider this also almost like PO2s character of oxygen. Okay. Now, these hybridized orbitals of carbon and oxygen will interact to produce some molecular orbitals of carbon monoxide, like this way. As I was telling earlier, that the 1s orbitals of carbon and oxygen will produce sigma 1s and sigma star 1s orbitals, and that will be below the main molecular orbital diagram of carbon monoxide. And for that, you can write just kk cell. I have not shown the diagram because of some space problem. If you want to show, that is also okay. Otherwise, you just write kk cell. Now, here in the main molecular orbital diagram or the frontier molecular orbital diagram, the first one will be the sigma non-bonding oxygen, because psi sp1 of oxygen is not interacting with any orbital of carbon, so it will be non-bonding. And then psi sp1 of carbon and psi sp2 of oxygen will interact with each other to produce sigma spx. As I said earlier, we are considering x-axis as the molecular axis. Then that these 2py and 2pz orbitals of carbon and oxygen will produce pi orbitals, pi 2py and pi 2pz. then it's coming the sigma non-bonding carbon, because psi sp2 orbital of carbon is not interacting with any other orbital, so it will remain as non-bonding. Then coming the anti-bonding orbital. First two is the pi anti-bonding, pi star 2 py and pi star 2 pz, and then finally sigma star spa. Okay, once we have drawn this diagram, we can now assign these as the molecular orbitals of carbon monoxide. So first, atomic orbitals, they are producing hybridized orbitals. Hybridized orbitals are then producing the molecular orbitals of carbon monoxide. Now we will fill the diagram with electrons. So we have total 4 plus 6, that is 10 electrons, because 4 electrons are already used in the KK cell. So we have to fill this frontier molecular orbital diagram with 10 electrons, and that will be positioned like this. Okay, so here sigma non-bonding carbon is the highest energy molecular orbital which has electrons. So this sigma non-bonding carbon will be the HOMO for carbon monoxide, and then these molecular orbitals, that is pi star 2 py and pi star 2 pz, are the lowest energy molecular orbitals which don't have any electron. So these are the LUMO, means lowest unoccupied molecular orbitals. Now again consider the molecular orbital diagram. From this diagram we can write the electronic configuration for carbon monoxide, and that will be sigma 1s2, sigma star 1s2, sigma non-bonding oxygen 2, sigma spx2, pi 2 py2, pi 2 pz2, sigma non-bonding carbon 2. Okay, so there are 8 electrons in the bonding molecular orbitals, 2 electrons in the anti-bonding molecular orbitals, and 4 electrons in the non-bonding molecular orbitals. But non-bonding electrons will not participate in calculating the bond order. So what will be the bond order? That will be Nb minus Na divided by 2. That is, Nb is the total number of electrons in the bonding molecular orbitals, and Na is the total number of electrons in the anti-bonding molecular orbitals. So it will be 8 minus 2 divided by 2, that will be 3. And this is in good agreement with the valence bond picture of carbon monoxide, where triple bond is proposed between carbon and oxygen. Now you see here there is no unpaired electron in the MO diagram, so carbon monoxide will be diamagnetic. This type of molecular orbital diagram can also be applied for some other heteronuclear diatomic molecules or ions like NO, NO plus or Cn minus. So first let us draw the molecular orbital diagram for NO. What I have done here, I have just replaced the carbon atom with the nitrogen atom. But one thing you should remember, that nitrogen has now one extra electron, because carbon has the atomic number 6 but nitrogen has 7. So these 2p orbitals will contains 1 electron each, and this extra electron will be placed in the pi star orbitals of the molecular orbital diagram of NO. So what will be the electronic configuration now? There we change here, okay, and carbon will be replaced by nitrogen, and it will be the extra electron, that is the pi star 2 py1. So what will be the bond order? You see here that total number of bonding electrons is 8 and total number of anti-bonding electrons is 3. So it will be 8 minus 3 divided by 2, that will be 2.5. And for magnetism, here you see one unpaired electron is there in the pi star molecular orbital, so NO will be paramagnetic. Now for NO plus. NO plus has the total electrons of 14, means it is isoelectronic with carbon monoxide. So the extra electron which was placed in the pi star orbital is now removed again. Okay, so the bond order will be the same as like carbon monoxide. So 8 minus 2 divided by 2, and that will give 3 bond order. Now finally for cyanide ion, here carbon has the atomic number 6 and nitrogen has 7. So there will be total 14 electrons, because there is one negative charge. Okay, and that extra electron is placed in the carbon orbitals. So the same concept, carbon will produce some hybridized orbitals and nitrogen will produce some hybridized orbitals, and they will interact to give the molecular orbitals of cyanide ion. And the electronic configuration will be sigma 1s2, sigma star 1s2, sigma non-bonding nitrogen, sigma spx2, pi 2 py2, pi 2 pz2, and finally sigma non-bonding carbon 2. Okay, so the bond order will be 8 minus 2 divided by 2 equal to 3, because total electrons in the bonding orbitals is 8 and total electrons in the anti-bonding molecular orbital will be 2. And the magnetism will be diamagnetic because there is no unpaired electron in the MO diagram. This is the summary what we have discussed. These are the molecular orbital electronic configuration. These are the bond orders, and you see here except NO all have the bond order of 3. Okay, and NO is paramagnetic, CO, NO plus and cyanide will be diamagnetic. Now let us consider NO and NO plus. Here you can see the bond order will be greater for NO plus as it has 3 bond order compared to 2.5 for NO, and bond length will be greater for NO than NO plus, because we know with the increase of number of bonds the bond length decreases. Okay, so for NO the bond length will be greater than NO plus, and bond stretching frequency will be more for NO plus as the bond order is greater. Greater the bond order, greater will be the bond strength, and that will increase the bond stretching frequency. So NO plus will have higher bond stretching frequency, mean higher stretching frequency than NO. Okay, that's all for this video. Thank you all for watching my video.